Okay, so we're going to be doing paper 2 for the year 2016. And we're starting off with question 1. And this is for June 2016. So the reactivity or the activity of a radioactive sample is measured over a 6-hour period. The results are recorded in the table. So here's the table below. Using the grid on page 5, plot a graph of activity A versus time. So it's always Y versus X, as you can see here. And what I did, I made sure to note my parameters before I go on to the next page. So knowing that this will be Y, I know we have to go from 0 to 80. And this will be X, so we have to go from 0 to 7. And to save time, I plotted my graph early. So what I did every 2 spaces for the x-axis is 1, 2, 3, 4, 5, 6, 7. So every 2 spaces. And then for the y-axis, I went up in multiples of 5. 5, 10, 15, 20, right up to 80. Then I plotted. So if we look at the other page, what I have here. Here's another page. So when it was 0, at 0 hours, you had 80 particles. So from 0, you go right up and you plot 80. At 1 hour, you had 50 particles. So 150. At 2 hours, you had 34.5. And likewise, we just keep plotting. So 34.5. Because each of these points is 0.2, it's 2. It's 32, 34, 36, 38. So, each point is 1. So this is 31, 32, 33, 34, 35. Right? So, because if 35 minus 30, you will get 5. And you have 5 spaces, so 5 divided by 1. 5 divided by 5 will give you 1. So you have 35 minus 30 give you 5. You have 5 spaces. So 5 divided by 5 will give you 1. So each space is worth 1. So it's 31, 32, 33, 34, 35. So between 34 and 35, you have 34.5. Okay, and that's what we did. That's what I did. I graphed and we got this nice curve. So whenever we're dealing with radioactivity, you're going to get a curve. And so I used my hand and I drew a nice curve. But you could also buy a helix. I don't know if any store is going to be open in your area, but you could purchase a helix. I'm trying to find my helix. So the helix look like this. This is what the helix look like. Okay? And you could manipulate it to bend however you want to get a curve or to find the best fit curve. So I got a helix and it's only about 11 EC. So you could get one. But I didn't use a helix for this, so this is my freehand. And then the next question would have asked. So the next question. The next question says, from your graph, determine the half-life of the sample. And how I did that, half-life is the amount of time it takes for a sample to decay to half its original amount. So it started out with 80 particles, and we need to go to half the original amount, which is 40. Half of 80 is 40. And I just went across, came to the line, and I pulled it down. So 40 and pulled it right down. And I got 1.7 because I have 1. And then in between here is 5, 0. So 1.5, 6, 7. So that was the half-life. So I wrote down 1.7 right here. Then it says, using your graph, determine a more accurate value of the half-life of the sample. So I just went on to find more half-lives. So half of 40 is 20. I pull it right across again. Across here. Came down and I got, you're going from the last part, the half-life before finish, to the new part with the half-life finish. So it's the space between the first half-life the end of the first half-life and the end of the second half-life. So this space between here is 1. This is 1 right here. 0.1, 0.2, 0.3, 0.4, 0.5. So I have 1.5 hours. And then I found the next half-life because half of 20 is 10. So I brought it across and I just took the space between here. So all of them is 0.1. So all of them are 0.1. So 0.1, 2, 3. This is 5. So that's 8, 9, 10. Then 1, 2. So 1.2 hours. Right? And so what I did, I added them up and found the average, which is 1.5 hours. Then it said, from your graph and using dotted lines, determine how long it takes for the activity of the sample to be reduced to 10 disintegrations per second from its original activity level. So from 10, I'm going to go right across to figure out the time and bring it down. And what I got was 4.4 hours because it's not the half-life this time, but the time it takes to reach 10. So from 10, you come all the way across and you bring down your dotted lines, and it's 4.1, 2, 3, 4. So I got 4.4 hours. I don't know how I have 4.5, but it's 4.4 hours. Oh no, it's 4.5 hours. See? Come right, that's where the line hit and come down, so 4.5 hours. Good. Now, then it says, state one reason why a line drawn through all the points would not form a perfectly smooth curve is because it's a random process, right? So it will happen. You could predict the shape of the graph because you know that it's gonna keep decreasing each time. But each time the number, if you did this experiment again, the numbers wouldn't be the same. However, this will decrease. The pattern will be the same. Just the numbers wouldn't be the same. Not you wouldn't get the same numbers, but the pattern will be the same. Now, all elements, including radioactive substances, have an atomic number and a mass number. Explain what the two terms mean. Well, the atomic number is the total amount of protons in the nucleus. It also represents the amount of electrons in a neutral atom. And the mass number is the total amount of protons and the neutrons present inside of the nucleus of the atom. Okay, in medicine, iodine 123 is used to check a patient's thyroid function. What does 1 to 3 represent? So 1 to 3 represents the mass number. And that's a wrap for question number 1. Good luck.